Okay. Let's get started. Let's open my PowerPoint. Dropbox. DIFC. Workbook. Physics. Atoms. Last lesson. You got paper, Go? You do. Open it. There we go. Quantum mechanics. Right. Got that? Yeah. We can start? Right. So. Okay, so. You remember this formula from fields. Newton's law of gravity. Now, what's interesting here is that in this picture, this formula tells you the force between the moon and the earth. And this formula, we didn't see it, but the formula can show you that it must move in a circle. Anyways, that's not something we did. It's possible for the moon to be here, here, or here. In fact, the moon could be anywhere. Okay, now, if we look at this picture is very similar, isn't it? We have a proton, an electron, we have this formula, and if we compare it, it's kind of the same thing, really, isn't it? Different constants, perhaps, different parameters, but the same form, right? However, something strange is happening here. We might think, therefore, the electron can be at any position. But it turns out it's not. Now, you knew this from chemistry, though. The electron can only be in different orbits. But that seems strange, because we don't say the moon can be in different orbits. The moon can be in any orbit. Whereas the electron can only be in certain orbits. That should seem a bit strange to you, because the formula is the same. Yeah? So, earlier, I told you a lie on purpose. I said that there's no smallest distance. There's no quantum of distance. Remember? I said there's a quantum of light. What do we call the quantum of light? Do you remember? Last lesson? Photon, yeah. Photon. Yeah, the quantum of light. I said there's no quantum of distance, but that's not true. There actually is a quantum of distance. And what will happen is the electron can be here, it can be here, but it can't be in between. Because there's a minimum distance, a quantum of distance. Yes, which matches up with the orbits. So, how do we get this idea? Now, in a moment you'll need to draw this, but I want to explain what's happening here. So if you have something called a black body, or something that's releasing white light, like the sun, and you pass this through a prism, you get a rainbow. Now you all know this, you all learned this in middle school. Let me draw it for you. You have a prism, you have white light, the light comes in, and you get all the different colours. Get the rainbow colours. Right? Rainbow. Yeah. Yeah. Now, what about if you have a hot gas? So, yeah, you have some hot gas. So because it's a hot gas, it glows bright. So some of the light comes out, passes through the prism, and you notice that you don't get all the colours of the rainbow. You only get some colours, but not all. Okay, that's interesting. And then the last one is if you have a cold gas and you shine some white light through it, so you put white light through it, and then the light comes out, and again you put it through the prism, and this time you nearly get all the colours, but some are missing. Okay, so you get missing colours.
Hot gas will.
Yeah, it's bright by itself. Is that what you're asking? Is that what you're asking? Yeah. Now, I want to explain, before you write anything, I want to explain why this happens. Okay? So, if you look at this hot gas, you have your atoms like this. Well, I'll just draw one atom. So, what's happening is these are moving around very fast because it's hot. Okay? So there's lots of energy here. Energy everywhere. In fact, it's kinetic energy everywhere. So these are moving around. Sometimes what will happen, you might have an electron. Let me draw. Sorry, I'll draw 3 lines. You might have an electron here. Now, what type of energy does this electron have if it's trapped?
Low energy.
Yeah, but it's positive or negative? Negative. Okay, now if I just go back to this picture for a moment, which energy level here is the most negative? Who's the most negative? 1. Okay, because it's the most trapped. And E4 is less negative. So E4 is bigger than E3, bigger than E2, bigger than E1. Yeah? Okay. So, what can happen here? These can sometimes drop a level. Now, if it drops a level, oh, come on. If it drops a level, what happens to its energy? Does the energy increase or decrease?
Increase.
Decrease.
Oh.
Decrease. It gets more negative.
Oh.
But conservation of energy says the energy has to be conserved. So what happens is if it drops, then it releases a photon. What energy will this photon have? It will have the same energy that was lost here. And you know that E equals HF. So, because you have certain energies here, then you get certain energies here, which means you get certain frequencies here, which means you get only certain colours. Each colour here represents a change in the orbit. So for example, maybe you get this colour because it goes from orbit 3 to orbit 2. Maybe you get this colour because it goes from orbit 5 to orbit 1. You know, each colour represents a different loss, a different fall in the orbits. Okay. Now, why does it not go up? Why does it never go up? Why does it only go down? Well, I'll give you a simple example. So, I know, I'll give you a good example I just thought of. Okay, so, here is the ground. Here you are sitting here. Your potential energy is negative. Okay? Only two things could happen. Either you will stay here, or you can fall down. And your energy now is more negative. Right? You can never fall up. You can only fall down. For you to fall up, someone would need to give you energy. So you can't fall up, but you can fall down. That's what's happening here. It can stay or it can fall. Sometimes it falls. Why might it fall? Oh goodness. Well, we won't go into too much detail. Sorry, it's stuck. So anyway, sometimes it can fall here. Right, what's happening in this picture? Well, again, we have our atom. And we have our orbits, which you learn about in chemistry. Yeah, so what happens is the white light comes in, and you could have your electron here. The light gives this energy. What happens if it gets energy?
Go up.
Right, yeah, it can go up, can't it? But this light that came in, it was taken by the electron so that it could move up. It's like the photoelectric effect. Remember, you have the metal, yes? The photon comes in, the light photon comes in, it hits the metal, and what happens? The electron is freed. But the photon, the light is gone, because the electron took it. Okay? So, the reason there's some colours missing here is because the electron took it. Okay?
What's electron?
Ate it. It took it in so it could move up an energy level. Yeah.
It
So
means lies.
it's gone.
Lies gone.
Yeah. The electron, it's like the electron ate it, gave it energy, move up.
Oh, you means electron eat the light.
Kinda, yeah. Now, it only eats the right frequency. So it needs some energy here to move up, doesn't it? So the energy it needs will equal E, which will equal HF. So delta E over H equals F. So you can think about it like this, Ben. It can eat frequency F. That frequency might be this colour. So why is this black? Maybe this is black because the light needed this energy to go from 1 to 2, or 2 to 3, or 2 to 5, or whatever. Okay. So these are missing because it needed to eat those frequencies to move up. Okay?
But the electron, it doesn't freeze.
If it gets enough energy, it can be freed.
Or is something like
Threshold.
oh.
Yeah. No, you're right, Ben. If it gets enough energy, it could be freed.
And what happened?
No, it doesn't. Yeah, no, it doesn't matter if it's freed or not. It'll still be black.
Okay.
So, for example, Ben, maybe this is black because this is going from energy state 1 to freedom. It doesn't matter if it's freed or not. Yeah. So, this simple experiment proves that the electron is in orbits. This only happens because the electron is in orbit. Okay? If the electron wasn't in orbit, then what would happen is all of this would be black. Because it would mean the let me start with this one. If the electron wasn't in orbits, then it would all be black. And this would all be a rainbow. Why would this all be black if the electron wasn't in orbits? Well, it'll be like this. Here's your proton, here's the electron. If the electron could be in any level, okay, what will happen is the light will come in, the electron will eat the light and move up a little bit. And because it can move any amount, well, then it'll take any light. So, if the electron couldn't be, if the electron could be in any orbit, then this would all be black because the electron would eat any light. Likewise, this would all be colourful if the electron could be in any orbit. Okay, because what will happen is the picture would be like this instead. Instead of being like this, it would be like this. So the electron is here, could fall here, could fall here, could fall here, release a little colour, release a different colour, release red, release blue, whatever. It could move anywhere and release any colour. Okay, so this proves that it's in certain orbits, because otherwise this should be fully a full rainbow, or this should be fully black. Okay, yeah. Another very interesting thing before you write this down, you know, you have in chemistry spectrometer, mass spectrometer. Okay, you have, I think, another spectrometer. I think it's called the light spectrometer. Do you know this one? So it's very interesting. What you do, you take something, I don't know, whatever, this thing, and you don't know what it is. You're like, what is this? Is it carbon? Is it hydrogen? What is it? And what you do is you put it in like a little box. You put it into the box and you heat it up and turn it into a gas, and then it starts to glow. Or you heat it up and you shine some light in it. So you do one of these two, and then the light comes out and goes and makes a rainbow. But some of the colours will be missing. The colours that are missing are different for each material. So I think, for example, if it was hydrogen, I think you get two colours missing in red, for example. If it was something like hydrogen and helium, you get two colours missing. So you can have this big computer, and it can have like a list of all the different materials and all the different pictures here, and then you just have to match it. So then you can say, oh, it is 20% carbon. It is, you know. So this is how you can find out what materials are made of. It's like, you know, this fingerprint. Yeah. Each material has a different picture here. It's like a different fingerprint. So it's very useful. It's very, very useful in science. Yeah. Okay, so these are called spectrums. This is the emission spectrum. Emission meaning releases light, and this is called absorption spectrum, meaning it eats the light. Yeah. Okay, do your very best to copy this into your notebook. You might need to draw one of these in the exam, or explain one of them in the exam. You look very unhappy, Gail.
How to draw a rainbow.
You can just write in words like rainbow with some colours missing if you need to. You don't have any colours? No. Okay. think Summer is still trying to print.
Yes, I don't know, but the machine is shit. I
Yeah.
used that last time. It just prints film paper. And it takes me like 2 hours.
Terrible. Right. Okay, we talked about this a little bit. Yeah. Okay, so here's a question. Right. You have an electron and it's in state 4. In state 4 it's minus 0.85 electron volts. And then what happens is it falls to state 3, minus 1.51 electron volts. So did it gain or lose energy? Lose energy. Where did that energy go?
Photon.
Yeah, it went to making a photon. The photon is released. My question is simple. What is the energy of the photon? So, what energy should the photon have? It should have E4 minus E3. Okay, so what's that? That's calculate, please. What's that? E4 minus E3. 0.6. What is it?
Yeah.
0.66? Is it?
Yes.
Yeah, 0.66. It's okay, girl. You look so confused. Not confused? It's okay? Alright. So that's a simple little question. Right. An electron is in the ground state. The ground state is called E1. It has minus 13.6 eV. It received a photon which made it jump to state 3. So it was in 1. Okay. A photon came in, ate the photon, up to 3 it went.
We need to know what's the energy.
Better. I need to know what's the frequency.
No, I mean.
First, you need to know the
Before.
energy.
Yeah,
Yeah. First, you need to know the energy. So first, you get the energy you need. Correct. And then after you get the energy you need, what formula do you use?
You say.
Yeah. Which? HF. Yeah. Okay. See if you can calculate the F, please. Give it a try. You got your calculator, Ben?
Yeah.
Yeah. Oh, girl, you still don't have a calculator. Hmm.
So E equals half. That's right.
E equals HF.
And H is 6.
You have it in from last week.
Yes, it's. It's E1 minus E3.
Yeah. No. E3 minus E1.
Why?
E3 is big, E1 is small. Bigger minus smaller.
Always bigger minus smaller.
Well, yeah, here. 8.1. Don't forget though, that's 8.1 EV. Need to convert it into joules first.
It's EV.
What is 8.1?
E3 minus E3 minus E1.
It's not.
Is not? Check again.
It's twice. Why? Where's
1?
8 come from?
I don't think you typed this in right, did you? Oh, it's gone.
It's just 1.
Minus 1.51 minus 1. No,
What?
it is 12, yeah.
Oh, yeah.
No, this is also calculated right?
Yeah, but I just wanted first E3 minus E1. Yeah, okay, 12.09, yeah. Then convert that into joules.
What's the answer first?
For with into joules? I don't know. Don't forget, I made you write the E at the front of your book. Ah, Summer, where have you been?
So,
Wait.
so I took Neil didn't in his office.
Okay.
Yeah, I just.
Okay, sit down.
I'm not sure. Like first we calculate the energy and over the H.
No, you didn't convert it into joules.
What is this?
It's wrong.
What is that?
It's wrong.
EV. Oh, it means EV convert. So it's tens. It's tens 1 times 6 over 2. Or
12.09 multiply E. Divide H.
okay.
Hey, English.
That's the class. Is it?
Better.
Let's do it.
Take a picture of the number. It's 1.1 times 16.
Hmm?
1.1 times 10, 16.
Final last the F.
Yeah.
Yeah, okay. What did you get, Gav?
I got EV, I didn't transfer it.
Oh, come on.
It,
Wrong. Sorry.
Oh my goodness. I thought this was an easy question.
1.603.
So you have to do
No, it's my So it's
E3
50.
minus E1
It's 3.
multiplied by E
Yeah.
over H. What did you get?
3 times 15.
Okay, good. Yeah?
Yeah.
Right.
Okay.
Now, okay, I want to draw something here for you. You have two things in physics that you care about.
Only 2 things.
Sorry.
What's this?
Four.
No, it's okay.
No, I'm trying to think of the right word. In physics, we study the behavior of two things. The first thing is waves, and the second thing is particles. They're the two things in physics we're interested about.
What's
Okay.
particle?
Particles, little mass, atoms. You know? So, for example, when we studied waves and fields, we were studying this. When we studied mechanics and electricity, we were studying particles. Yeah? Oh, and also when we studied materials. Okay? So the question we'd like to know now is, how do you know which one you have? There's a very simple experiment here. What you do, you have two slits and a screen. Oh, come on. Where'd it go? There we go. And you have something, we don't know what it is, so I'll call it mystery item. If it's a particle and you fire it between the double slits, some of them will go left, some of them will go right. Yeah, some of them will bounce away, but some will go left and some will go right. And we shall have, if we have a machine here, a detector, it can see and measure that there's some here and there's some here. So it sees that there are two and it says it is a particle. Now, if you have something here that's actually a wave, some will go here, some will go here. But you remember from our lesson that what you get is something here, and then here and here, and then here and here. You don't get two dots, you get more than two. Okay? Remember, this is called a fringe. Fringe. So then your detector here will say, you have, this said you have two, and this one says you have more than two. So it will tell you you have a wave. So it's a very simple experiment to know, is it a particle or is it a wave? It's very simple. Yeah. So before I continue, in the exam they sometimes ask you to explain this experiment. It's called the double slit. So the picture will help remind you. In the experiment of the double slit, if you have a particle fired through the double slit, you will get two fringes. If you have a wave fired through the double slit, you will get more than two. You'll get a fringe pattern. This means you have a wave. Now, I think it would be good for you to write this down. Double slit. Got that somewhere? Boat? Did you get your lab report printed at least?
It's very difficult.
Yeah, I know. Life is very difficult too.
Yes.
Okay, continue. Continue. Yes? Alright, so electron gun. It fires electrons. Double slit. Screen. What picture will I get here? Will I get A, 2, or B,
A.
more than 2? So is it going to be A or B?
A.
A or B?
A.
A. Why?
Electron is particle.
Yeah, electron's a little particle, so you get A, because it'll go left or it'll go right and you get 2. So you'll be surprised to learn that you don't get A.
Wow.
Yes, you actually get B, which is surprising. Very, very surprising.
Electron gun.
Yes, so you fire the electrons
But how do we make it?
and you get some electrons here, some here, some here, some here, some here.
And it's similar to
It's the same.
the same wave.
It sounds away. Now that's strange, right? That is very, very strange. What happens is the electron comes in, some of them go this way and land here. Maybe some of them go this way and land here, and maybe some of them go here. Most of them will go in the middle. So you get a big collection here, and then less here, and then maybe 1 or 2 here and here.
We need very high speed electric guns.
No, it can be slow.
Is that about weight?
Oh, it gets stranger. It gets stranger. So, you might say, okay, what is happening? How can the electron go over here, some here, some here? How can it do that? So you might think, I know what I'll do.
The force.
Maybe it's a force, we don't know. Yeah, maybe something's pushing it left or right. I don't know. So you decide to put a little, like a little machine to detect, basically to watch. So I'll just draw an eye here. See. So we'll do electron blue. So you say, okay, what's the electron going to do? So the electron comes in, and then some go this way, some go this way, and now you have 2. You have 2 now, because you were looking. If you turn this machine off, I'm not joking, it goes back to many.
What?
Yeah. 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 Yeah, I know. So I'm going to show you a little video on YouTube. There's a nice little animation that shows this. So now you should be thinking, does the electron know it's being watched? Because that's what it looks like. If you try to watch which way the electron moves, it moves like a particle. If you don't watch the electron, watch,
Your eye
Yeah.
is shooting something light.
Yes, you might think that. Let's have a look. How do we search? Here we go. This sounds terrible. Double D-O-U-B-L-E. Oh, space. No, not space. How do I do backspace? Goodness. Slit. S. L. Now it's only 5 minutes. It's kind of a children's animation. It's 5 minutes, but it's really nice to see this. Don't want it too loud.
And here we are, granddaddy of all quantum weirdness, the see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now, there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern.
This is what Ben taught.
They decide to shoot electrons
Slowly.
one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange netherworld of quantum events. What is matter? Pulse or
There
waves?
we go.
And waves of what? And what does an observer?
Interesting, right? Very interesting. So, the electron knows it's been looked at, right? Now tell me, there wasn't in the video, but you could also do this. You have somebody here, right at the end, looking only here, right at the end. So what happens is it behaves like a wave here. Behaving like a wave, and then here it turns back to behaving like a particle at the last minute. Yeah. So it can behave like a wave all the way up to here, and then because you're looking here, then it will switch back to a particle at the last part. Yeah, which is quite strange,
Why?
right? Yeah.
Why? No reason.
Who knows? It's just what it does, you know?
I'm waiting for the reason and the video is finished.
Yeah, there's no reason.
Okay.
This is just how it works. This is just the way it works. It knows if it's being observed. It changes its behavior.
Jeez.
Yeah.
That's
If
scary.
it's being observed, it will behave like a particle. If it is not being observed, it will behave like a wave. Simple as that. Why? How? No one knows. No one knows.
How about just maybe put some camera outside the field?
So tell me what you're thinking. Where would you put it? Let me go backwards.
Like same as video, but you put like far away, but like really that side. But it's a good
Oh.
camera.
Over here?
Yeah.
Oh, far away.
Yeah, and you can see, but you can zoom in or zoom out. You can observe. Just leave the field.
Ah. Oh, so like you put like a camera here,
Yeah.
far away. Oh, I see what you're saying. And you can zoom in, zoom out. So like maybe this could be like 10 meters. Is that what you mean?
Yeah.
Or whatever.
I
Yeah.
don't think the particle can still.
And you're not here. You're gone. And you leave it. And you, yeah, I see what you're saying. You turn this on, and you go.
Yeah.
Oh, interesting. So what do we think? Wave or particle?
Wait.
Particle. Particle. Because the camera is observing. Yeah. Yeah. Now
Just scared.
I have one more for you. Okay. So, you have two things. This screen. Okay. Okay. This screen is connected to a PC. And then here you have your detector here. And this is connected to the PC. So, after the experiment, you get two files. File 1 is the screen. So maybe it'll look like this, or it could look like this. Okay? And then file 2, you get information about if the particle went left or right. So maybe file 2 could be, like this one here, it went, left, right, right, or, it could be something like left, left, right, right, left, 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 right, right. It tells you which way the particle went, for example. So it's a file like this. Okay? So you turn the machine on, and you get both files. What will you get? You will get A or B. You'll get A, because you have the observer, so it looks, sees, oh, it goes left, goes right, left, left, right, left, right, and you get this picture. Okay? So we can have, if you record file 1 and 2, you will get a situation A. You'll get a particle. Okay? Situation 2, you only record file 1 and you have no file 2. So you turn this off. What will you get? Yeah, you'll get a wave. Okay, here's the interesting one now. Number 3, last one. Okay, you record file 1 and file 2. You delete file 2 and keep file 1. So you have this on and this on, but after you make file 1 and file 2, you delete file 2. What will you get? Wave or particle?
Yeah.
You're going with wave because both machines were on.
Yes.
Yeah. You will get particle. Yeah. If you delete file 2 and never look at it, if you never look at file 2, if you delete it before you look at it, it goes back to being a particle. So the electron knows if you deleted its observation.
So if I just put a camera
Yeah.
uh,
Yeah,
and,
yeah.
and then turn off that,
Yeah.
turn off that,
Yeah.
it's particle or wave.
If you just have a camera,
Yes, and turn off that.
turn it on or off.
Turn off the camera.
Oh, turn off the camera, it's a wave. Turn on the camera, it's a
It's
particle. Turn on the camera, but don't look at the picture.
Yeah.
Delete the picture.
Yeah.
Particle.
What's delete?
Delete.
Um,
What's delete in Chinese?
删除。
啊？
删除呀。
删除，清空。
看它关机一下。
Too much Chinese.
Huh?
Delete.
It's not turn off.
No,
turn
delete.
off.
Look, delete.
It's this. It's
Yeah.
not the PowerPoint.
No,
it's
this, delete.
this.
删除键。
删除，删除。
Yeah.
So how about if you mark the electron before
Ah.
you put in electron?
Good. If you mark it, like if you could put a little mark on it,
Yeah.
and then what do you do after?
You can see in the screen. Maybe put different color or something.
Ah, yeah, well then I think it'd be a particle then. Yeah. 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 But you can't mark electrons. But if you could, it should be a particle, I think.
They're scared.
It's very strange, isn't it?
Why? It's
I told you quantum mechanics is difficult.
It's teachers.
Yeah. 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 Very, very strange.
today is 2019,
Yeah.
and we don't have the reason for this.
No, this is just what it does. This is just the way things are. You know, it's like saying, why does it fall? Because of gravity. Why gravity? Well, just, that's the way it is. Yeah.
You mean something will source wave?
Yeah, so the idea here is that particles, small particles like electrons, they will be a wave if you don't look, and a particle if you do look. So it's not just electrons, it's also protons and neutrons and all of this stuff too.
But the gravity have reason. We know the reason. It's one thing. It has the little.
Yeah,
Little-
but the thing is, Summer, why? Why do big things have more gravity?
So if one thing have a large
Yeah.
mass and a little velocity.
Yeah. No, I know. But there's no reason for that. It's not like just because you have mass, you should have gravity.
But
It's not like maths. 1 plus 1 equals 2. Must be this. Okay? In physics, it's not a must. You know, it just is. That's just the way it behaves. Yeah? It's strange. I know. It's strange. It's very strange. It's very strange. So, this was discovered maybe 100 years ago. 100 years ago, roughly. Yeah. An electron or any small particle may act like a wave, and you can calculate its wavelength. Its wavelength will be h over p. And remember that p, does anyone remember what p is? Small p? Small p is momentum, mv. Yeah? So you can say that lambda equals h over mv. So if the m is very small, then the wavelength is very big. And this is why they used electrons in the experiment, because electrons have the smallest mass. So it makes the biggest wave. Okay. So this is called de Broglie's formula. Yeah.
We don't have to draw that thing down.
No, that's okay.
So yeah, it's in terms of the I. P2 minus P1.
No, just MV. No, not P2 minus P1.
I mean, it's
It's same.
the same.
Yeah, same thing. Yeah. All right. So, an electron gun fires electrons at a speed of 0.1 c towards a screen 1 meter away. What is the wavelength for this electron? Okay, so we'll draw the picture. Come on. Right. You have your screen. This is 1 meter. You have your electrons here. And their speed is 0.1 c. And if you don't look, they'll behave like a wave. So no looking. And we want to know what is their wavelength. So it's h over mv. H you know. me you know, I gave it to you. And the v is 0.1 c. And c you know. Okay, so give me the wavelength, please.
So why did you give us the 1 meter?
Oh, for the next part later.
I think
What's wrong?
So I mean, it's 1.60 to 10 minus 19.
No, that's no. That's the E.
No mass.
2.26 times 10 minus 6.
Yeah. Thank you, Ben. Right, B. These electrons are fired between a double slit where the D here is 10 to the minus 10 meters. What is the angle of the first order? So you'll have some here, you'll have some here, you'll have some here. Do you remember this? This is n equals 0, n equals -1, n equals 1. And my question is, what is the angle here? This is when we studied waves. The formula is n lambda equals d sine theta. Do we know n? We do. What's n? I want the first order. So what's n? N is 1. Do we know lambda? We do. Do we know d? We do.
Yeah, well,
I want theta. Give me theta.
oh,
七次方，
啊，
八次方。
七次方。
0.1是什么
Uh,
Wait a second, I get
Is that C is
3
power of
times
8.
10 8, yeah.
Is 8.
Sorry, it's wrong.
What's wrong?
2.4
2.421
times minus 11.
11.
Ah,
Sorry.
okay. Give me the theta, please.
It's 0.1c.
Theta, please. Theta now.
Okay, so it's we just sine inverse or whatever.
Well, the theta will be sine inverse n lambda over d.
The only lambda. because
Yeah, the n
it's
is 1. And the d is... No, the d is 10 minus 10.
Oh.
This is big D.
Okay.
You got it somewhere?
No.
Why not?
14.
14? Okay. And lastly, C, I want to know the fringe separation. You know the distance between the fringes, the x. So I think you had a formula x equals, if I remember, lambda d over d. Was that it? Wasn't that the formula for in waves? You know, guys, look.
Yeah, lambda.
Oh, I used s instead. Okay, well, sx, whatever. It's going to be 2.42 times 10 to the minus 11 times 1 over 10 to the minus 10. So that's going to be 2.42 times 10 to the minus 1, which is 24.2 centimeters. Which is, you know, pretty far apart. Yeah? It's okay?
Yeah.
Yeah? Right. Lastly,
Where is the x?
that's the distance between these.
So you can use the x.
Yeah, x or s, whatever. X. What? The last thing I want to talk about, you might remember this when we did waves, but you know what a microscope is. You know, you look in here, there's your eye, and this here is very small, and you can see it, quite large. Okay. How big can you see here? What scale? The rule is you can see anything that's about the same wavelength as the light you're using. So for example, if this light has wavelength lambda, then you should be able to see things which are about the same wavelength. Not really, it's not as good as this, but just roughly. So if you're using light that's maybe 10 to the minus 6, well, no, maybe. If you're using 10 to the minus 6 meters, well, then maybe you could see something that's maybe about 10 to the minus 5 meters. You know, roughly. Maybe 10 to the minus 6, but probably not 10 to the minus 5. Okay? So if you want to see smaller, then the wavelength here needs to be smaller. Okay? Smaller, yeah. So for example, if you use a wavelength like 10 to the minus 10 meters, then maybe you could see... Guys, are you listening to me? Are you listening? Okay, well, look like you're listening, please. If you want to see something smaller, then you use a smaller wavelength. So if you use 10 to the minus 10 meters, then maybe you could see something like 10 to the minus 9 meters. Okay? If you want to see really small things, then you need to use a really small wavelength. So you could use electrons. Electrons have a small wavelength. So if you use this electrons, then maybe you could see 10 to the minus 10 meters. So this is how you can see atoms. You can kind of see atoms if you use electrons. You can get a picture of what the atoms look like if you use electrons. Okay, so this is called an electron microscope, and it uses electrons. And the wavelength of an electron is 100,000 times shorter than visible light. This means electron microscopes are 100,000 times more powerful than a normal microscope. You can see 50 picometers. That's how clearly you can see. Google what picometer is, and you can see how clearly you can see. 50 picometers. That's how small you can see. How big is it? PICO.
What is Armstrong?
10 minus 10. What is it?
12.
10 minus 12.
Yeah.
Yeah. An electron microscope is used to see very small, to see on the very small scale, i.e. 50 picometers. This is because the wavelength of the electron is very small. Okay. So it's about the same. Okay, so an electron microscope is used to see on the very small scale, i.e. 50 picometers. This is because the wavelength of the electron is very small. You can write that down.
Stephen,
Yeah.
this morning we had a 3-hour class.
Yeah,
What's the next?
we'll do maths.
And, little break?
What?
Do we have a little break?
I'll give you a little break after you try some questions.
Oh,
And if you're good,
I'm not. I just slept 2 hours.
you're bad.
Or I see the on the
Very small scale. Sorry, very small.
Scale.
SCALE.
No. I.
Right, so that was the quantum mechanics. Difficult ideas, but only one formula. Lambda equals h over mv. It's the only formula. I like this question in the exam because the exam question is kind of easy because all you're doing is, you know, E3 minus E1 is simple calculations. Question 1 and 2 are like exam questions. Question 3, try it, but it's difficult. But definitely 1 and 2 you should do. Problem, Summer?
How to calculate this?
Oh my goodness, the first question, you just minus.
Just one.
Look, Summer, it goes from E2,
Yes.
which is minus 3.4, to
Oh,
E1.
Okay.
Goodness sake.
We need change it.
Sorry, Summer, that was the easy question.
Okay.
Change to joules.
For the first one, no, but for the second one, yes.
You say how much energy?
Yeah, so you can use EV for that, but for calculation in number 2, you'll need to use joules.